Hello everyone. So today I decided that I want to work on a slightly smaller project, a interpreter for a small Haskell-like language in Rust. So far, all that I've been able to get going is a simple echo system that the line repeats back, that the program can repeat back what you say, and we have our parser, which uses nom combinators. So I will just open the documentation for nom. This is a nice little command. Um, the make there is a bit special. I'm using I will have to make a video about my setup, my BIM setup. So I have nom now open on my second monitor. So I want to parse very simply. Let's write up some tests. I want to test parsing an identifier, right? So let's say we have a parse identifier function. Now for nom, now a nom, how to explain this? Now a nom, now to use a nom function, we take an input that is a string. And let's see. Complete input. So an identifier we can define as, let's see. Let's say there's a to-do there. Now, if I remember correctly, nom has an I result. You know what, I'm going to show you fine folks the documentation. So we have alpha, and we notice that a nom parser returns this I result. And so an I result is effectively just a wraparound result with a tuple inside of it. Now for our case, we want to say that the parser returns an I result about a reference of string and the output type here will probably itself be a string for now. I'll work up into syntax trees later. So when we parse an identifier, we want to assert equal that when you parse an identifier of x, it should return an OK. OK with no more input and an x. Now if we try to compile the test here, I remember, I think maybe it's this. Is it this? My apologies. Not, I'm a bit rusty, so to speak, about this. So let's see. So a nice resource for learning Rust is the Rust book. Now you want this one here, the book, the book. And we need to find test ink. Let's see if we can error handling, common collection, smart pointers, fearless concurrency. I thought they had a section on testing. Oh, there it is, number 11, automated testing. How to write tests. Okay. Ah, I know why, I think. Okay. So now if we open up the main, notice that I haven't declared this as a module. So if I get the module, so if I import the parser module, unresolved imports. Okay. Well, we can see that we want it's combinator, not combinators. It's the singular, not the plural. And then it's unused. Or let's see, this is, maybe if I just change this to iResult. This function is never used. Let's see what happens if I were to compile this. Expected 0 arguments. Parse Identifier. Oh, I see. This needs to be called Parse Identifier test. And then we cannot find it, so we will have to say here, this is a very common trick for test modules. Found in enum, returns a stir. Right, so this here needs to be a full string. So we say toString. The reason we make it a string now instead of keeping it a stir is because making it a string will let us later not worry about the input data. Okay, so we're now at the point that we actually need to parse an identifier. So let's see what we can get. We know this is what we want for our first item. We want at least one alphabetic character, and then we will probably want alphanumeric characters, 0 or more. So now to sequence these and add them together, we would grab, well, let's see if the sequence module has anything for it. We have sequence. Separated pair, tuple, pair. We'll probably want pair. And then we can map over the tuple, right? So this is the power of knob. So we can take those two, and then we can map over the, I think we can just call map. Map should be fine. There'll be some very tricky type warnings in here. There may be some tricky type warnings. So we will want, so we'll use iResult. We will also want to use Combinator. So we will want to grab map. And so we will take the result of the pair, which is in sequence, first string we want character complete. And we can try and use alpha 1. So we will pair together alpha 1. You notice that it immediately tries to hand us an input with alpha numeric 0. And now you'll notice that it's mismatch type because the map needs some function to work the input over. So let's call this the first and second parts. And we return format, which will contain first and the second. And now we just call this with the input. Now if we make the test, as you see, the test passes. Now we will also want to make sure that this fails, so we can say 1, 2, 3 should not pass. Now to say that this should not pass is to say that there's an error in here. And the error type for nom contains an error struct. I should also say here use nom error. As you can see, we're missing fields. So for the input field, we can just say 1, 2, 3. And the error kind I do not know. However, that means I can get away with something here. I can just assert matches. As you can see, now we can just say that this is an error. We don't care about the internals, we just care that it is some sort of error. Make that test, it still passes. Now I'm going to take this test and put it down here and say that we have 12y, and make sure that this also passes. There. And so you can see we now can parse an identifier. Yep. Now you'll notice that we're operating solely on characters. If there is a desire, I can I can make a short video describing different kinds of parsers, but for right now, I think I will focus on doing this. So now that I have an identifier, I need to parse an expression. So when we parse expressions, so this is where we may want to start defining a syntax. Let's make the syntax.rs. So syntax.rs, we will need some sort of enum for expressions. All expressions. The only two expressions we have right now are identifiers are literals. We will write the definition for that later. Identifiers. And currently we'll have lambda as well. And a lambda has a parameter that we shall call an identifier. And it has a body, which is some boxed expression. The reason we need to box the expression here is to not allow an infinitely sized type. And so we need to define what is an identifier. Right now, the type identifier will just be equal to string. And the reason that we separate literals and identifiers here is that they need to be treated differently. Identifiers, you need to read the value, whereas literals, you can just look at the literal itself. Effectively, identifiers mean that in a context. Now we will also need a binary operation, binary expression, which will have a left-hand side that will be a box about another expression. We will also have a right-hand side, which will be a box about another expression. And then we will have an operation, which will be the we'll call it a binary operation. Now we will have an enum for binary operations. However, this enum won't be much simpler. Here we can have so on and so forth, but what I will say is that at this point we can definitely make function calls, or let's call it application, as a binary operation. So let's try back to the parser. So when we want to parse an expression, parse expression test, this will be an identifier type expression. And we will now use the syntax expert in here. And now we need to tell main as well that we need syntax. Now this one, here, this one will not parse as an identifier. This one, when you parse this as an expression, there should not be an error. It should also be an OK. But we will say that this is some literal, and that literal well, now we have to make a decision. What is a literal? What is a literal? Well, a literal will probably be another enum that we'll need. A literal can be a, well, for right now we'll just have a boolean, which will contain bool, and we'll just allow integers for now. Integer, and that we will store as a, let's just say that it's an I64. So here we want a literal integer, getting 1, 2, 3. I think it would be easier to just star this. And here we should be importing from the crate level. And we will parse an expression here. And we will parse a lambda x. That just returns x. Which then this will parse to an expression. That will be a lambda. Missing body. Let's say the parameter of this lambda will be just and finally we'll need the body, which will be some owning pointer, and this owning pointer will point to an expression, which will be an identifier, which will take in x to string. Okay, now we just need to write this parse expression function. So now we take our input. It's the same. It's effectively the same type declaration as upstairs. And then we return an I result, same thing, which returns a reference to a string. And this time, instead of returning a whole string, we want to return an expression. Assert eq. There. That error was a bit strange. Now let's try parsing an expression. Well, let's think about how we will want this. Let's write a few more tests, right? So one test that I'd like to make sure of is that if I write, say, this, that the body is itself a lambda. As you can see, the body is a lambda. This lambda will take a parameter y, and instead of and we can take in an identifier that shall be called x. I will have to add a ton of convenience functions onto this. And finally, I will want to say something like this followed by y should not be an expression lambda. It should be an expression, should be a binary expression where the left-hand side argument is this. Now we need the operation on the left-hand side. Well, the operation can simply be a binary operation application, because we're applying this function. And finally, the right-hand side can just mean expression identifier, which will take y and now here we have to box this. And we will also have to box this. And now we will need to make sure that this becomes a string. Let's see what happens if we have an error. Well, we notice that this type is not correct. So let's think. We have our expression, and we want to parse. Well, we will probably first want to parse lambdas. Because function applications have a higher order. And that reminds me, I should also be able to say that if I write f of x, this should be a binary expression with the left-hand side being an identifier, which is f.toString, and this can just become the right-hand side. And we'll need to pass in the operation, which is just a binary operation application. So now that we have enough test cases, we should try to parse. At the furthest out, we should try to parse lambdas. Then we should try and parse function applications. So this should parse lambda, take some input, Now you'll notice that I prefer having a that if I have a root parse expression, it generally just has a call to one item, because when you talk about precedence hierarchies, it makes sense to do this, to have your top level just be parse expression, and then you name every expression going down. So return expression. So here we can do the other style that this permits, where we say input and expert is equal to, we want to parse a primary expression. We can now parse a function application. Not necessarily. Because when you parse lambdas, we need to check that the next thing ahead is a slash. So we can say that we want to get we want to use that. And so we want to do the same thing up on top of the combinator. We want to say that this parser that's coming up is optional. In fact, we probably want to do this as alt, which we'll need branch for, which is a different set of things. And let me just read the documentation again. So we have pair here. I'll just move around a bit. So we have multi. We don't want multi, we want branch. Yes. And alt. Takes list of parsers one by one until they succeed. Right. So at the lambda, we want to do an alt where the first parser we have is actually a lambda, and the second parser we have is something lower down. So we'll go back to the code. So alt will either take parse application, or it can take sequence tuple tuple So first we consume 0 more spaces, then we consume a slash, then we consume 0 more spaces again, then we consume a single identifier for now. Then we will consume 0 more spaces, then we consume an arrow, which in this case we want tag for that. And finally, we will then parse a whole other expression. Now we want to map this, so we will say we will map this tuple result and we notice that space 0 is not here, but we can just say that complete should give us space 0 and tag as well. Tag is not resolved. Okay. So I will check my documentation. Tab, bytes. Huh. Strange. That's interesting. I thought tag was... I remember... Okay. Recognizing byte streams. So tag apparently comes from bytes, which will be in now you'll notice here we have a huge amount of items. So we don't care about the first thing, because that's the string. Don't care about the second thing because that's the slash. I'll just notate that. Fancy little trick in Rust to prepend with an underscore to ignore it. Now here we have our single parameter. We don't care about this other space. We'll call this the arrow. And then we have our body. So I just need to add branch up to this list of imports up here. Now here, let's just add that we can return an expr lambda, missing the fields of body and parameter. Well, the single parameter here is going to be the param. In fact, I can simplify this by just saying that the parameter is the parameter that we have, and the body is a box of the given body. There. Now we need to be able to parse applications. So to parse the application of a function, it's going to be the same type signature as the rest of it. Expr. Okay. So now we need to figure out how do we parse an application. Well, we know that an application is just two expressions right next to each other. However, they'll probably need to be primary expressions. So let's say that we will call these primary expressions. And an application will always have some input now I will show the other way to use nom, which could be called which you could call, say, the sequential way. So we get our first expression here, and then we say then we will want to do a Combinator optional so an optional combinator, and the optional combinator will sequence together a few things. we will make a pair, mostly because I can get away with saying space 1, and then we will also do another primary expression. Not find space 1. Well, that's simple because I can just import it by saying that we have complete space 1. Let this be the input and optional parameter, right? So now if we have some parameter that is equal to the optional parameter, now the one thing to note here is that we probably don't want pair because we're going to drop the space. So we should say preceded, which then means we can just not drop the parameter. And we have our else. Now, in the case that we don't find a parameter, we'll probably just want to return our expression. Otherwise, we will probably want to return some expression, which will be a binary operation. And we will have here a left-hand side, which will be the same, which will be a boxing around our given expression. And this we'll place with the right-hand side, and this will be the parameter. And finally, we now get here, and our operation can be a binary operation application. Binary expression. Now you'll notice that we have type errors, so we can say that we want OK, taking an input, and our value. Unclosed delimiter. Ah, there. Now we get to reformat this. There's probably a better way to write this, but for right now, I will just leave it at that. And finally, we get to parse a primary expression. Well, to parse a primary expression, we can say that we will parse based solely on alternates. And the alternates we have are things like parsing an identifier. However, we can't just parse an identifier. We need to map its result. So we'll need to say something like Combinator map. And we map the result of this. That will become now an expression. Identifier ID. Also here we want to parse a number. Now I want to read a bit of the documentation here for nom. So let's see, if we have a number and we're complete, when we say that it recognizes an integer, what do they mean by that? Let's say we want an I64. Endianness. Ah, this takes in raw bytes. That's not what I want. I want characters. So we can probably go to characters, complete. We will want to say digits. For now, we will just focus on getting normal digits working. So let's try adding that. So we want to Combinator map digit 1 the value, and we will say that we want an expression literal, a literal of type number, or no, integer value. Cannot find digit 1. Well, that is simple. We can just call complete digit 1. We will have to read this a bit later. Now we'll probably want this. Furthermore, we may want to do parenthesized expressions. So parenthesized expressions will definitely be a sequence thing. And they will be delimited. So the first thing we want is a character paren. Then we want to parse an expression. And we want a closing paren. When we make the test, as we can see, there's a lot of issues. But let's try reading through them slowly. So if we take the first issue at the top, char is not allowed. Okay. Char does not exist. So we grab, so if I remember correctly, we had character in here. Yes, we did. And instead of space 0, well, we could probably leave space 0. We've got some useful things here for it. Useful things here for it. And let's see what our next error is. We'll just ignore the unused for now. Trait input length is not implemented for 64. So let's see. We return a digit 1. So when we return a digit 1, we will return a result. Input take at position. Let's see, if I go to Combinator, I want to map the result of an output. As we can see that this only cares about the output of the original parser. So this here will return chars, I think. Let's add an explicit type binding and see what it's actually returning there. Let's see, I think it's returning documentation should be returning that. There we go. Look at that. Adding an explicit type annotation sometimes actually helps. So here, we now need to parse an I64. Well, that seems like a Rust thing. So if we look up stir in Rust here, can we parse? Stir parse. Parses the string into another type. Whereas as long as this is from, whereas the type, as long as the type is from stir. We have implementations for all of our cool types, so let's try using it. We may have to map, not opt, but we may have to map a bit trickier. Ah, we want a result here, eh? Okay. Let's try this, because this sounds like, yeah, even, look, even their little example does that. Okay. So we want to map res. What we can do instead is here we'll say value dot parse, and we will then dot map into it x, which we will say that's an expression of a literal. A literal is a literal number, or no, integer of x. Now, as you notice, I think I can just remove this type here. Type annotation needed. Okay, so I do need a type annotation there. But you'll notice that the rest of it seems pretty fine. Let's see what happens if I make the test. Ah, there are all sorts of issues. So let's get a better look at this. So if I run the testing, first item we run into is that here. These are the same type, but you cannot equate them because this expression here cannot be equated. Okay, that is a good point to make, that if you want to test something, you will need to make sure you can check it for equality. So we want to derive partial eq on it. The problem is now that we need to derive partial eq here. In fact, here, I want to derive partial eq and clone. I don't need clone just yet. Partial eq. Let's run the test again. Does not implement debug. So these need to implement debug now, do they? These can be debug. Ah, as you can see, a test failed. And that is on line 104 of the parser. So it failed. This item failed. Let's read the error. So the input is X, and the character was returned. Right. Okay, so let's see. In a primary expression, we may want to parse identifiers. So let's see, when we parse a lambda, we take 0 spaces, we parse an identifier, we then parse an expression. Check one thing. Okay, there is no preceding space. Maybe there is an issue with the preceding space. So the way to solve that would be saying that could be something like Ah, okay. So we've got the correct output, we just don't have it right. What line is that? 128. Let's see, so we have an application with a lambda and an identifier y. And the reason this is erroring is because it thinks the body is just an x. Hmm. Because it thinks the body is just an x there. It is correct that the body is just an x. Huh. I think I'll be fine writing that as a test. So this needs to be just an identifier. Wait. Delete everything here. Delete everything here. Delete the space. There. So now if I build a test, ah, that was nice. Look at that. Able to write a nice little parser. Now to make sure that these aren't all so yelly about it, we can just make this one public. Then we'll go here. And we will try to parse an expression out of the given line. Well, in fact, we'll order the parser to parse an expression. And here we will match on the result. And non-exhaustive patterns. Okay. So in the OK case, we have an expr. What we will do is we will print it out. And so here we'll just call this remaining. Expert does not implement display. Well, we're not intending to display it. Remaining is unused. Well, we can just say there's remaining. Now if there's an error, E, we'll just print that out as well. Okay. So now when we build, we can have cargo run. As you can see, identifier X. And then we can do \x, arrow X, Y. Parsing error. We'll have to work on spacing later, but let's see if we can do Y. There we go. Look at that. And we can use Control D to end. And I will just write a little git commit. Thank you for joining me. It's been a pleasure to have you.